Okay, so good day. For this video, we will be discussing concavity and inflection point. So when we say concavity, so concavity is the behavior of the curve, okay, for which it is curving inwards. Okay, so it's basically a curve, but for uh, graphical description, so we will only describe concavity based on its direction, if it is upward or downwards. Okay, so concave downwards looks like this. Okay, so as you can see, the orientation of the curve is concave downwards. Okay, so it's the curve is facing downwards. Okay, so if we try to enlarge this, so maybe it will look like concave downwards, so somewhat looks like that. Okay, so as you can see, it's facing downwards. The curve is facing downwards, so this is concave, sorry, downwards. Okay, so also for this one, so it may not be obvious because the concavity is smaller, so but let's try to exaggerate it. So if we draw it like that, so you can see that the curve is facing upwards. Okay, so this is an example of a curve which is concave upwards. Okay, so comparing this one, so this one and this one, okay, so those two curves, so you can see that those two curves are increasing, okay, from left to right. Okay, so those two curves are increasing, so therefore both of their first derivatives are positive. Okay, so however, the first derivative cannot be used to describe if it's concave downwards or concave upwards, because as you can see, both of these, the slopes of the tangents are both positive. Okay, however, as you can see, if we try to look at the rate of change of the slope of the tangent lines, so you can see that if it's concave upwards, okay, so let's say we have these tangent points. So as you can see, as we go from left to right, okay, the slope of the tangent increases. Sorry, the slope of the tangent increases. Okay, so as we go from left to right, we can see that the slopes of the tangent lines are gradually increasing. Okay, and on the concave downwards, we can see that the slopes of the tangents are gradually decreasing. Okay, so since the rate of change of the slope is associated with the second derivative, okay, so then we can determine the concavity of a curve over a given interval by its second derivative. Okay, so uh, it may also be called as a second derivative test. Okay, so testing for concavity. Okay, so to test for concavity, okay, so to test our concavity, we use the second derivative. Okay, so if the second derivative is greater than 0 or positive, like what we have here in a concave upward curve, so as you can see, the slopes are increasing. So first the slope is like this, and then like that, and then like that. So the slope increases. So if it's greater than 0, therefore our curve is concave upwards. Okay, and similarly, if it's decreasing, the slope is decreasing, okay, as you go from left to right, so the second derivative is less than 0 if it's concave downwards. Okay, so that's it. Okay, so it will be similar with the first derivative test, where we determine the interval for which the function is increasing or decreasing. So for the second derivative test, we can also use it to test for concavity. So to determine the intervals for which the curve is concave upwards or concave downwards. Okay, so to determine the intervals, so we also need to find the inflection point. Okay, so the inflection point is the point where the curve changes from concave upwards to concave downwards, or vice versa. Okay, so in this case, in our drawing, so we have here from left to right, so the curve is concave downwards. Okay, so you can see here it's concave downwards, and then at this point, at the inflection point, so it changes from concave downwards, so it changes from to concave upwards. So that is the inflection point. Okay, so since at concave upwards, the second derivative is greater than 0, and at concave downwards, the second derivative is less than 0, so then the inflection point, which is in between the concave upwards and concave downwards curve, so therefore the inflection point is where the second derivative is 0. Okay, so that's this lesson is all about. So basically, for this video, we will be determining the inflection points as well as the intervals where our curve is concave upwards or concave downwards. Okay, so that's it. So it will help us to graph our curves more easily because we know the orientation of the curves, okay, if it's concave downwards or concave upwards. Okay, so let's have some examples. Okay, so let's solve these examples. So find all the points. Okay, so sorry, so this is wrong grammar. So since find all the points, so this should be plural, so therefore there should be no parenthesis. Okay, so find all the points of inflection and determine the open intervals where the function is concave up or concave down. Okay, so for letter A, so we have function of x is equal to x cubed minus 3x squared plus 3. Okay, so solution for letter A, to solve for the inflection point, so solve for inflection point. So let us recall that at the inflection point, our second derivative is 0. So set f double prime of x is equal to 0. Okay, so since we have the function f of x is equal to x cubed minus 3x squared plus 3. So taking its first derivative, so f prime of x is equal to, so derivative of x cubed with respect to x, that is 3x squared. Okay, minus 3 multiplied by the derivative of x squared, we have 2x, and then plus derivative of a constant, we have 0. Okay, so simplifying, our first derivative is 3 x squared minus 6x. Okay, so next for our second derivative, so derivative of 3x squared, so that is 3 multiplied by the derivative of x squared, so that is 2x minus 6. Derivative of x with respect to x, that is 1. So therefore our second derivative is 3 times 2x, so that is 6x, okay, minus 6. Okay, so since we set the second derivative to 0, so therefore 6x minus 6 is equal to 0. Now solving for x, so transposing negative 6 on the other side, so we'll have 6x is equal to positive 6, dividing both sides by 6 to solve for x. So therefore x is equal to 1. Okay, so since we are solving for the point, so we must also solve for f of x at x is equal to 1. So at x is equal to 1, so f of 1 is equal to, so substituting in our original function, so our original is x cubed minus 3x squared plus 3. So that will be 1 cubed minus 3 times 1 squared plus 3. So this is 1 minus 3 plus 3, so that is 1. Okay, so therefore inflection point is at 1, 1. Okay, so that's it. So that's the inflection point. So the next is solving for the intervals where the function is concave up or concave down. So with that, we will still use the number line, okay, so that we know what are the intervals. Okay, so this is the number line for x, and we have our inflection point at x is equal to 1. So therefore, so if this is 0, okay, this is 1, 2, and so on. This is negative 1, negative 2, and so on. So our interval now will be divided by the inflection point. So we have two intervals. So from x is less than 1 and x is greater than 1. So those are the intervals for which we will determine if it is concave upwards or concave downwards. Okay, so therefore for the first interval, so for the first interval, that is from negative infinity to positive 1, so that is negative infinity is less than x is less than 1. So say we choose any number between negative infinity and 1. So let's say that is negative 1. Okay, so say x is equal to negative 1. So using the second derivative, for which the second derivative is 6x minus 6, so f double prime of x is equal to 6x minus 6. So f double prime of negative 1 is equal to 6 times negative 1 minus 6. So this is negative 12. Okay, so since the second derivative is negative, okay, in this interval, from negative infinity to 1. So therefore, from negative infinity to 1, the curve is concave downwards. Okay, so this is concave downwards. Okay, so it's that easy. So next, for the next interval from positive 1 to positive infinity, so we can express that as 1 is less than x is less than positive infinity. So the second derivative, which is 6x minus 6, so we will select a value of x between 1 and positive infinity. So say x is equal to, say x is equal to 2. So f double prime of 2 is equal to 6 times 2 minus 6. So that is positive 6. So since it is positive, the second derivative is positive, okay, in this interval. So therefore, between negative 1 and infinity, the curve is concave upwards. Okay, so to summarize, so we have inflection point at 1 1, okay, so it is concave downwards at negative infinity to x. So negative infinity is less than x is less than 1, and it's concave upwards, okay, from 1 to positive infinity. Okay, so this is our answer. So this is the point of inflection. Okay, the point of inflection is at 1 1, and then our intervals, it's concave downwards from negative infinity to 1, and concave upwards from x is 1 to positive infinity. Okay, so similar with increasing and decreasing functions, but this time we will be using the second derivative test, okay, instead of the first derivative. Okay, so for our second example, is we have, so this one, f of x is equal to x to the fourth minus x cubed minus 3x squared plus 4. Okay, so getting its first derivative, so deriving this, so this will be 4x cubed minus 3x squared minus, so since we know that we're gonna be multiplying the exponent by the numerical coefficient, so 2 times 3, that is 6x raised to 2 minus 1, so that is 1. So no need to write it if the exponent is 1, and then plus 4, so which is basically 0. So next, we can now solve for our second derivative. So second derivative is, so 3 times 4, that is 12x squared minus 2 times 3, that is 6x raised to the power of 2 minus 1, so that is 1, and then minus 6 multiplied by the derivative of x with respect to x, that is 1, so minus 6. Okay, so this is now our second derivative. So to solve for inflection point, so we need to set our second derivative to 0. Okay, so therefore 12x squared minus 6x minus 6 is equal to 0. So we can factor out 6. So what will remain inside is 2x squared minus x minus 6 is equal to 0. So we can eliminate 6 by dividing both sides of the equation by 6. So what will remain is 2x squared minus x, that is minus 1. Minus 1 is equal to 0. Okay, so the next is factor this. So how do we factor this? So since we have a numerical coefficient together with x squared, so we can multiply the coefficient of x squared with the constant. So 2 times negative 1, this is negative 2. Okay, so the product, if you multiply this, so this is negative 2. Okay, so factor negative 2 such that the sum of the factors is negative 1. So that is equal to negative 2 times 1. Okay, or 1 times negative 2. Okay, so therefore we can decompose negative x into positive x minus 2x. Okay, so we'll have 2x squared plus 1, so that is plus x, and then minus 2, so that is minus 2x. Okay, minus 1 is equal to 0. So this is still the same with this. If we simplify this, correct, so it's still equal to x squared minus, it's still equal to 2x squared minus x minus 1. Okay, so this one. Okay, so but here we separated negative x into plus x and minus 2x so that we can group them and then we can factor them later on. So grouping this, so we'll have 2x squared plus x plus negative 2x minus 1 is equal to 0. So getting a common factor for the first group, greatest common factor is x. So what will remain here is 2x plus 1. Here greatest common factor is negative 1. So minus inside the parentheses it will be 2x and then plus 1. Okay, so because we factor out the negative, so is equal to 0. Okay, so now we have a greatest common factor of 2x plus 1, and then what will remain inside, so if you factor out 2x plus 1 from this, so what will remain is x, and then if you factor out 2x minus 1 from here, so what will remain is minus 1, so is equal to 0. So that is the complete factor of this. Okay, so next is equate the factors to 0. So we'll have 2x plus 1 is equal to 0, and also x minus 1 is equal to 0. Then solving for x here, so we'll have 2x is equal to, transposing negative 1, dividing both sides by 2, so we'll have x is equal to negative 1/2. On the other side, transposing, so we'll have x is equal to 1. So we have 2 inflection points. So one is at x is equal to the negative 2, and then the other one at x is equal to 1. Okay, so we have 2 inflection points. So but first we will solve for its corresponding f of x. Okay, so f of negative 1/2. Okay, substitute in the original function. So we have negative 1/2 to the power of 4 minus negative 1/2 to the power of 3 minus 3, and then negative 1/2 squared, and then plus 4. So that would be, so using our calculator, so negative 1/2 is negative 0.5, I think. So we'll have negative 1/2 raised to the power of 4 minus negative 1/2 cube, minus 3 multiplied by negative 1/2 raised to the power of 2 and plus 4. Okay, so 55 over 16. Okay, so at x is equal to 1, so f of 1 is equal to 1 to the power of 4 minus 1 cube minus 3 times 1 squared plus 4. So 1 minus 1, 0 minus 3, and then plus 4, that is 1. Okay, so therefore the inflection points are at, so negative 1/2 and then 55 over 16. And at 1, 1. Okay, so if this is correct, so let me double check that again. Negative 1/2 raised to the power of 4 minus negative 1/2 cube minus 3 times negative 1/2 squared plus 4. Okay, so that's correct, I think. So next is solving for the determining the intervals for which the function is concave downwards or concave upwards. So similar with what we did earlier, so the inflection points will divide the intervals. Okay, so say for example we have here our negative 1/2, then we have here our 1, and then let's say we have here our 0, and so on. So negative 1, negative 2, here we have our 2, 3, and so on. So our interval will be divided into 3. Okay. Okay. So first is we have from negative infinity to negative 1/2. So for negative infinity is less than x is less than negative 1/2. So say x is equal to negative 1. Okay, so using the second derivative, our second derivative, so this one, so our f double prime of x is equal to, so let's rewrite that, 12x squared minus 6x minus 6. Okay, so say our x is equal to negative 1, so therefore we'll substitute that in our second derivative. So we will have 12 times negative 1 squared minus 6 times negative 1 minus 6. So that is equal to 12 multiplied by negative 1 squared minus 6 times negative 1 minus 6. So that is positive 12. Okay, so since it's positive, therefore this is concave upwards. Okay, so so for the next interval from negative 1/2 to 1, so from negative 1/2 is less than x is less than positive 1, so we can say x is equal to 0. So f double prime of 0 is equal to, substituting in our second derivative, so 12 times 0 squared minus 6 times 0, minus 6. So we have 0, 0, so negative 6. So since our second derivative is less than 0, so therefore, for this interval, this is concave. That is concave downwards. Okay. So for our last interval, from positive 1 to positive infinity. So for 1 is less than x is less than positive infinity. So say x is equal to 2. Okay. So f double prime of 2 is equal to 12 times 2 squared minus 6 times 2 minus 6 is equal to, so 12 times 2 squared minus 6 times 2 minus 6. That is positive 30. So similar with the first interval, this is concave upwards. Oops, sorry. Okay, so this is concave upwards. So therefore, if we summarize the answer, so in here, together with the inflection point, so it's concave upwards at negative infinity is less than x is less than negative 1/2. Okay, and from 1 to positive infinity. So 1 is less than x is less than positive infinity. And this is concave downwards from negative 1/2 to positive 1. Okay, so that is our answer. Okay, for the inflection point and the intervals. Okay, for which the curve is concave upwards or concave downwards. Okay, so for the last example, so let's have letter C. For letter C, that was f of x is equal to 3 over x plus 1. Okay, so deriving, so f prime of x is equal to, so using the quotient rule, so the derivative of u over v is equal to v du minus u dv over v squared. So denominator multiplied by the derivative of the numerator minus numerator multiplied by the derivative of the denominator divided by the denominator squared. So we have denominator x plus 1 multiplied by the derivative of the numerator, which is 3 constant, so that is 0, minus the numerator 3 multiplied by the derivative of the denominator. Derivative of x plus 1 is 1 over x plus 1 squared. So our first derivative is, you can simplify that as this is 0, so that is negative 3 over x plus 1 squared. Okay, so next, second derivative. So still using the quotient rule. So denominator, we have x plus 1 squared multiplied by the derivative of the numerator. Okay, our numerator is negative 3, or we can have written it as negative 3 on the outside. So negative, so 3 over x plus 1 squared, so that we can write the negative sign here. Okay, so derivative of 3 is 0 minus 3, derivative of the denominator. So by using the general power formula, so we'll have, so multiplied by 2 times x plus 1 raised to 2 minus 1 multiplied by the derivative of u, which is inside the parenthesis, times 1 over x plus 1 squared. Okay, so simplifying this, we will have negative. This will become 3 times 2 times 1, so that is 6. Negative 6 times x plus 1 over, sorry, this should be denominator squared. So since our denominator is x plus 1 squared, so this will be x plus 1 squared and then squared. Okay, so the denominator will be x plus 1 raised to the power of 4. Okay, so therefore our second derivative is positive 6 over x plus 1 cube. Okay, so that is our second derivative. So therefore, solving for the inflection point, so at the inflection point, the second derivative is equal to, sorry, the second derivative is equal to 0. Okay, so therefore 6 over x plus 1 cube is equal to 0. Okay, so we don't have any values for x that will satisfy such equation, because if we cross multiply the denominator on the other side, it will become 0. So what will remain is 6 is equal to 0, which doesn't make, sense. Doesn't make sense. Okay, so therefore you don't have an inflection point. So there's no inflection point. Okay, so we have graphs that don't have inflection points. Okay, so but how would we determine if the function is concave upwards or concave downwards over a given interval? So if we recall our original equation, okay, so this is actually a function that has a discontinuity. Okay, so meaning it's a value of x for which the graph does not exist. Okay, so there is a discontinuity. So let me rewrite that. So for f of x is equal to 3 over x plus 1. So it's actually discontinuous at, if it is discontinuous if we have a value for x that will make this function indeterminate. Okay, so that will exist at x is equal to -1. Why? Because at x is equal to -1, the denominator becomes 0. Okay, and 3 over 0, that is undefined. Okay, so therefore we have a discontinuity at x is equal to -1, and that is now our that now will divide our interval. So at x is equal to 0, so this here is our -1, -2, then here 1, 2. So it's discontinuous at x is equal to negative 1. Okay, so therefore we have two intervals. For the first interval is from negative infinity to negative 1. So negative infinity is less than x is less than negative 1. So here from negative 1 is less than x is less than positive infinity. Okay, so those are our two intervals. Okay, so testing using the second derivative. So for negative infinity is less than x is less than negative 1. So say x is equal to negative 2. Okay, so using the second derivative, so our second derivative again is equal to 6 over x plus 1 cube. So we'll have 6 times divided by negative 2 plus 1 cube. So this is negative 6. Okay, so therefore at that interval it is concave since it's less than 0, so therefore it's concave downwards. Okay, so next for the next interval from negative 1 to positive infinity, so say x is equal to 0. So x is equal to 0, so f double prime of x, okay, of 0 is equal to 6 over 0 plus 1 cube, that is positive 6. Okay, so it's greater than 0, so therefore this interval is concave. This interval is concave upwards. Okay, so to summarize, so you have no inflection point. It is concave downwards at negative infinity to negative 1. And then it is concave upwards from negative 1 to positive infinity. Okay, so that's it. So I hope you have understood the points of this lesson, and good luck and see you on the next videos.